Hi everyone, in this video we're going to go through the SAC2 prep questions. So there's 3 questions here, kind of similar format to your actual SAC in the way that you have to not just answer a question and there's a right and a wrong answer, but explore what is actually happening. So your result for your SAC will obviously depend on you demonstrating your knowledge. So it's just not a matter of answering the question and moving on. Kind of think about it as an English essay. If you were responding to a text, you just don't answer the essay question and you're done with it. You need to show your understanding of the text. So in your SAC for methods, or your SACs for methods, you need to show your understanding of the content, not just answer a question and get it right or wrong. Okay, so question number 1. Use rectangles to show that the area between the x-axis and the curve f of x is equal to the area between the y-axis and the inverse of f of x. All right, so first of all, we've got our original function, f of x, and I'm going to plot that, and I'm also going to plot the inverse. So first of all, we need to get the inverse. So I'm just going to get my pen ready. All right, so if our function is f of x equals x minus 4 cubed on 27 plus 10, remember if you're finding the inverse, then we switch x and y. So f of x is the same as y, so I'm going to make that one now x, because remember we switched them for the inverse. And then we just need to solve for y. So I'm going to take away 10 from both sides. Now this isn't actually a hard one to do. It probably looks a bit more complicated than what it needs to be. Over 27, then we're going to multiply both sides by 27. Now I'd probably do this in less steps than what I'm doing now. The opposite of cubing is taking the cubed root. So the cubed root of 27 x minus 10. Whoops, make that a little bit longer. Just remember your radical, which is your the square root sign, or the cubed root in this case, has to cover everything. Don't be sloppy in your exam. Or don't be sloppy in your SAC, but I'm a little bit more forgiving than your examiners. All right, so we're nearly, oh God, that's a terrible x. We're going to add 4 equals y. Now, you should really go the next step and take the cubed root of 27. So the cubed root of 27 is 3, and then we're taking the cubed root, so that's kind of like a times, but we don't tend to write that in, x minus 10, and just make sure that plus 4 is on the outside. So I'm going to plot both. Oh, one thing that we always forget. Now, there's nothing wrong with putting this on the end, but you must have that inverse notation there if you're finding the inverse, or you could even put it here. All right, probably don't need it twice, it's a bit silly, but you can't leave it as y equals. You would hate to go to all that working out and forget that notation. And remember, your examiners, I know you're not doing the exam just yet, but your examiners are looking for marks to give you, but they also need to separate students. So if you can't put the inverse notation there and someone else does, well, they're basically saying, well, they know it's the inverse and you can't display that you know it's the inverse. So make sure you use the correct notation. All right, so let's plot both of these on Desmos, and I might just pause it so I can write them down and you're not listening to me just waffle on. All right, so here is the graph of the original function, which is in blue, which is a cubic, and in green, I've got a cubed root graph. So remember when you did your first SAC, we, well, one of the questions will ask you to explore why an inverse exists. So remember, it has to be 1 to 1. So this cubic is a 1 to 1. That's why we can take the inverse of it. So if you had to find the inverse of a function, remember it has to be 1-to-1. So if it's not 1-to-1, you would restrict the domain. Okay, so this is 1-to-1. And remember your inverse is reflected along the line y equals x. So if it helps, you can put the line y equals x like I have there in purple, so you can see, well, it's the same on either side of that line. All right, I'm going to take that off. Okay, so there's our two graphs. So just because I need to sketch some rectangles on there, let's just make it a... Okay, all right, I'm going to just copy... All right, dog in the background making noises. All right, where am I going to put you? It's not going to let me paste it anywhere nicely. Okay, I'll just do it on the next page. What am I doing? All right, and let's do the inverse. This is where I probably should pause the video again. All right, so obviously you would need to sketch them by hand because you don't have access to the computer during your SAC. All right, so this is the graph of, where is my pen? This is the graph of f of x, and this is its inverse. Okay, so the question is basically saying, well, the area under f of x and the x-axis is equal to the area between the y-axis and its inverse. So I'm just going to go from, I don't know, I don't want to do too many rectangles because we don't have all day. All right, might do 4 rectangles. So actually, I think I can draw a straight line. Let's just get rid of that for a sec. Let's see if it's going to work for me. Nice rectangle. All right, so let's do left rectangles. Oh, seriously, that was a pretty good rectangle. I was going to leave it like that. Won't worry about doing it. Here we go. I thought I would know that I was wanting to draw a rectangle, but obviously my line wasn't straight enough for it. All right. Let's just do 3 because we'll be here all day. So I've gone from 1 to 4. So the width of each rectangle is 1. All right, and then I would go ahead and calculate the area of these rectangles. All right, so basically what it's saying is the area here is the same as if I was to go from 1 to 4 from the x-axis. All right, so this time I did left rectangles because we're doing the inverse. It's the right that is going to hit it. So, and you can kind of see at x equals 1, we hit the rectangle here. All right, so there's our corners, a bit hard to see on that third one. So that means that we've got to hit it there at 1. All right, so you are doing the inverse, but in case you forget, just check it. Just see what it looks like. Should be pretty much the same as the blue one, just on its side. All right, so there's our 3 rectangles. It's a bit hard to see. Finding the, I don't know why I'm shading it in, but we're finding the area of those 3 rectangles. Now remember your inverse. I'll just go back up here. It's quite a complicated one. X minus 10 plus 4. So that is basically giving us the y coordinate. So what we need to do is when we're looking for the area of each rectangle, right, we've got 3 rectangles. The width is the same, so you can just take that out as a common factor, and it's always going to be the same. And then each point, so the first one's going to be f of 1 plus f of 2 plus f of 3. All right, writing it all out. Actually, I've defined f of x up here. Sorry, I was talking about the inverse and then I went and wrote about the original function. So here's your original function. All right, so instead of writing that 3 times, or if you chose 5 rectangles, you're writing it 5 times. And also it depends on which rectangles you choose, left or right. What am I talking about now? Okay, I feel like I said something wrong before, but I can't remember what I was saying. Okay, so if you're finding the area of this, we'll do that in the calculator in a second. Let's just go along with this. All right, so when you're doing the other way around, so basically we're going, instead of having vertical columns, we've got horizontal bars, I guess. The point here is we've got to find the corresponding x coordinate. Okay, so that x coordinate, if you think about your inverse, so our inverse is, and I wrote it down, I might just write it down again. Oops, 3 times, it's not 3 cubed, it's 3 times the cubed root. Just make sure you don't make that mistake. Plus 4. Now, if we wanted to find the x coordinate, so remember this is y equals. So, you know, for the first one, it was easy because it was already y equals. But now you need to get it as x equals. So x equals, and what does x equal? Well, if I went ahead and just rearranged that to get it in terms of x, I actually get my original function. All right, so if you wanted to, you can rearrange that to see whether it's correct, but x is equal to f of x. All right, so this point here, actually you can't see my, I always point, but I know you can't point. This point here is just f, probably shouldn't write f of x, f of y. No, what am I doing? Hold on. It is f of x, but I'm going to be substituting in y. So x is equal to, just trying to think the best way to do this. X minus 4, no. Sorry, I'm just getting a little bit lost. So x is equal to, when we rearrange this, we're going to have y minus 4 cubed over 27 plus 10. So before I said x is equal to f of x, but you're, instead of having x, you're switching x and y, if that makes sense. Because we're doing the inverse. All right, so this first point here that I've highlighted in blue is going to be the same as f of 1. All right, because I'm substituting 1 into, keep pointing to things, into this. And for this side, I'm substituting 1 into f of x. Okay, so you're basically getting the same value both here on the y-axis and here on the x-axis because you've taken the inverse. All right, so then we've got plus f of 2 plus f of 3. Now, it is important that you do show that this exists, what x is equal to. Okay, so you need to show that, and then you're making that connection that the area of the inverse is the same as the area of your original function. All right, so if you wanted to go ahead and do that on your calculator, let's just clear everything. Okay, so let's put define into your calculator. Let's define that function. All right, and then we've got x minus 4 cubed over 27 plus 10. And you can't see that on my calculator, so I'll just drag it down. All right, so your area is 1 times f of 1 plus f of 2 plus f of 3, just so we don't have to type it over and over and over again. All right, I get 86 on 3. Where are we? 86 on 3. 86 on 3. And leaving it as a improper fraction is fine. Now, if you want to leave it as a mixed number, all right, I always find it. There we go. It's 28 and 2/3. But 86 over 3 is fine, 28 and 2/3. Now, don't go giving me any decimal numbers unless it specifies. Okay, unless it actually says round, or if it's a terminating decimal. So if it was like a half, that's fine because it's just 0.5. But something like this, where 2/3, where 6 is recurring, you need to write it as a decimal. All right, and that is the same as this one. All right, but basically I've shown that with the blue box. Okay, and with my pictures, you probably won't have time to, in your SAC, to do more than that. But if you had more time, you might want to go explore something else in more detail. As for the number of rectangles, I probably wouldn't do just one. So remember, you need to show your understanding of what is happening, but you're also just doing it in your calculator. So doing 3 or doing 5, it takes, the time difference there's not much difference because you're just doing it in your calculator. If you were doing it by hand though, obviously writing that 5 times is going to take a lot longer than writing it 3 times. So I wouldn't try to impress me by doing a lot of rectangles, but just doing 1 is probably not going to cut it. All right, let's move on to question 2. Actually, did I answer that question? I can't remember. Yep, so we had to show the area. Now, if you wanted to do the exact area, I'm just trying to think. No, I'm not going to do that. All right, let's move on to question 2. All right, so in question 2, we've got 3 different functions. We've got 2 parabolas. Oh, no, sorry. We've got 1 parabola, a cubic. I think in class yesterday I said we had 2 parabolas, not actually noticing this X out the front. So we've got a parabola, a sine graph, and a cubic. So use any of the functions used above to show that when approximating using rectangles, the approximate area gets closer to the actual area as the number of rectangles increases. So a question like this, if I was answering this, I would set up a table. I love tables. So you might do f of x, g of x, and h of x. And then you got your actual area. And then we might do 3 rectangles, 5 rectangles, 10 rectangles. Is that too many? We'll do 10. Now, it doesn't matter, actually. The width does matter. So I'm just thinking whether we should do... Actually, I might change those number of rectangles soon. We'll just see. Okay, so got an actual area. Then I've got 3 rectangles, 5 rectangles, 10 rectangles. The other thing I need to do is where am I going from? So I probably should have written that somewhere. So I might just do from x is going from 0. Now I probably should have seen what they looked like before I decided. Actually, let's write them all in. Okay, I'm going to pause and put them all into Desmos. All right, I've got all 3 functions now on Desmos, and I might just put them all in. So you can see there that they all go. Yeah, so 0 is probably a good starting point, and maybe go to 10, I reckon. Let's go to 10. What's that one? Oh, no, not 10. Let's go to, kind of is that 6 there? Maybe I'll go to 6. All right, so 0 to 6. Where am I? All right, so I'm going from 0 to 6. I'll do the same for all of them just because I can, but you don't have to. Yeah, because you're basically proving, you're looking at each one separately. So you're using each function separate on their own. So I'm doing 3 examples of why it works. So you could do 1, you could do 2, you could do 3. All right, so I'm going from 0 to 6. So if I had a width of 1, I would have 6 rectangles. So I might just change these. Sorry, if I had a volume of 1, how many rectangles did I say? It's 5. 10, and then we'll do 20. So basically, if we've got 5 rectangles, we've got a width of 1. If I've got 10 rectangles, I've got a width of a half. And if I've got 20 rectangles, I've got a width of a quarter. Okay, so it's definitely the rectangles are getting smaller. I'm getting more rectangles, the rectangles are getting smaller. Unfortunately, I can't draw them. Actually, I don't know how to draw them on Desmos, so I'm not going to draw them. But if you were doing this in your SAC, you probably should draw them. All right, I'm just going to, I don't like my scale here. Let's go to 10. 1. Where did it go? There we go. It's a little bit easier to see there. Where are you? Okay, so we'll have a look at the parabola first. So I'm going to look at that. So annoying how when I go to copy and all right, so there's my parabola. I'm going to do, I might just do sketch just the one, otherwise this video is going to go on forever. All right, so if I had 5 rectangles, we're going from 0 to 6, so here's 6, and I can choose left or right. I'm just going to go left. So there's 1, there's 2, a bit wonky, there's 3, there's 4, and there's 5. All right, so there's your 5 rectangles. For the next one, I've got 10. Oh gosh, how am I going to draw this? This is going to be very hard. All right, so oops, probably should start it that way. There we go, there's 1. There's 2. So you can see they're basically getting thinner. All right, if you were drawing this on your SAC, obviously you would need to draw them a lot bigger just so you can draw all your rectangles in. All right, and then you would keep going to 6, and then for 20 rectangles, clearly I have not left myself enough space, so I'm not going to draw that in, 20 rectangles. If you were doing this on your SAC, you might want to start with fewer rectangles. So maybe going from 0 to 4, so you've got 3 rectangles and you're going up to 6 and then 12. But silly me, didn't do that. All right, so on your calculator, where is the calculator? Okay, we're going to go to define again, and I'm just going to put that cubic in. And what have we got? Negative x minus 4 squared plus 36. Just always do a double check that you've got everything put in correctly. All right, so my actual area. So I'm going to do definite integral from, go down for me, 0 to 6. No, we're going from 0 to 6. What did I do? 1, 2, 3, 4. No, I didn't go to 6. All right, how embarrassing, I can't actually count. Let's just rub that out, sorry. I don't know, in my head, I think I was going from 1 to 6 and then not really taking any notice. All right, so we've got 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Okay, on our calculator, going from 0 to 6 of f of x dx. All right, so the actual area is 192. My dog in the background is growling. All right, so if we're doing 6 rectangles, each width is 1. So we're going to do 1 times. And we've got f of 1 plus f of 2 plus f of 3 plus f of 4 plus f of 5. And we don't put in 6 because we're doing left rectangles. Oh, I didn't do f of 0 at the very start. F of 0. All right, 0, 1, 2, 3, 4, 5. All right. So I get 185 with 6 rectangles. Now you can see it's also quite time consuming putting it into your calculator. So I probably wouldn't do this many rectangles. Now you can just go and add to that. So instead of writing it out again, we're now doing a width of a half. So I'm going to do 0.5, change my width. And the 0, 1, 2, 3, 4, 5, 6, sorry, 5 stays. And then we've got the halves. So we're going to do f of a half plus f of 1.5 plus f of 2.5. Surely there's a quicker way of doing this. F of 3.5, f of 4.5, and then f of 5.5. I feel like I probably made a mistake with all that. Let's just see how we go. 188.75. And then if I was to do 24 rectangles, which I'm not going to do because it's going to take forever, obviously that would be closer to 192. Then you could go and do g of x exactly the same way. Again, I wouldn't choose this many rectangles. It's going to take you forever to do. And, you know, with the question, it says use any of the functions. So if you're short on time, just do one. But do remember that you're showing your knowledge. So maybe having more than one is better than someone who has just chosen one. But you've also got to consider use of time in the SAC. So you don't want to spend all the time doing a question like this and then not finishing the SAC. All right, question B. Use any of the functions used above to explain under what conditions you would be overestimating the area under that curve and when you would be overestimating and underestimating. All right, I'm going to use the parabola again just because we've got it printed here. And I'll do it down here. Skip that. All right, make that a bit bigger. And I'm going to do 2 of them just to compare left rectangles and right rectangles. I need a space in between. Okay, so if I was to use left rectangles, now might be a good idea also. Where are we? I'm just going to draw a line down the middle. So I think halfway is at 4. And halfway here. Okay, and this one I'm going to do left rectangles. Oh, it's a terrible spelling of left. And this one I'm going to do right. Excuse me. All right, so left rectangles, remember you go from the left, and I'm going to go all the way. I'll do that. Oh, I'll start from here. Okay, so I'm going to start, well, down here at -2, and then we're next here at 1, so let's go up there, and we're at 0. All right, I probably should put the vertical lines on. Oops, it's a bit wonky. And then on the other side, still doing left rectangles. So it's called left rectangles because the left corner of the rectangle is hitting the curve. It's a bit wonky. There we go. Oops, why am I doing that last one? I did that one wrong. Gosh. Oh, I've done them all wrong. Oh my God. Sorry. It's getting late on a Saturday. And, well, that's no excuse. But... All right, so you can see on this side, it's increasing. All right, the function is increasing. So remember, you're a little ant going in the X direction. If you're going up, you're increasing. So we're also increasing on this side. And then let's do the decreasing in pink. On this side, we're decreasing. All right, the function's decreasing. Little ants going down the hill. Okay, so with left rectangles, when it's increasing, you can see we're under the curve. So we're under approximating. All right, use the word approximating because we're actually approximating, not estimating. And then when it's a decreasing function, you are over approximating. Terrible handwriting, but you know what I'm writing. Okay, so you can see that. Now with right rectangles, so when you're drawing a right rectangle, always go from the right side. So at 10, we're just going to go there, and let's see how quick I can do this. Oh God, that's a bit wonky. Obviously not too quick. Kind of like stairs, aren't they? Okay. I don't think you can hear my dog in the background. Or she does all day is sleep. She's just growling. She's probably thinking, why are you keeping me awake with your maths? Okay, so just make sure everyone there haven't made any errors. All right, so right rectangles means your right rectangle. Oh, sorry. Right rectangles means your rectangle is touching the curve on the right side. So you can see now when we're increasing, it's the opposite. We're over approximating. And when we're decreasing, we are under approximating. Okay, so yeah, so parabola is a good one. You probably wouldn't do it with a function that was always increasing or always decreasing. So let's just have a look at our functions. The cubic, the cubic has parts where it's increasing and decreasing, which is good, and the sine graph obviously does as well. So you could, use any of them. If you had time, you could even go one step further and work out and show those values. So you've shown it visually, but you could also find the exact value and then show that from -2 to 4, it's less than, so your parabola is symmetrical, all right? So from -2 to 4, it's increasing, but using left rectangles, you're under approximating, so you could work out what that is. Whereas with right rectangles, you're over approximating. It wouldn't actually take you that long to do because they're kind of like the opposite of each other. So you're not really doing a lot more work, but again, it does take time. So you've got to consider whether you have time to do something like that in your SAC. All right, question 3. Now, similar questions like this appear on the exam. Sometimes you're given a rectangle to do. Sometimes it's a triangle. So sketching that, let's just quickly sketch it. 16 minus x squared. We'll get rid of these. I've got to press it so it comes on. There we go. All right, so there's our parabola. And I'll just, come on. So I'm just going to put this here. Okay, so basically it said we've got a right angle triangle is formed using the x-axis and the point UV, and U is between 0 and 4. So obviously the base of the triangle has to be between 0 and 4. We don't know what that is. So when you're drawing your triangle, if you wanted to draw your triangle, that is, just go to any point, go up. Oh, that looks like it's at 10, but it's not. Don't let that fool you. All right, that's the point UV. Okay, so we don't know what that is. That could be anything. All right, it's just that point is in just terms of U and V. Now, if we had to write V in terms of U, we just substitute U into the function. So U f of U, which is U 16 minus U squared. Okay, so they're, oh gosh, they're your 2 points. So with our triangle, I'll draw that over here. It's a right angle triangle. The height is 16 minus U squared and the base is U. So I've just sketched it. It'll probably take you a little bit longer. Write V in terms of U, I did that as well. Determine the maximum area of the triangle. So the area of a triangle formula is a half times base times height. So we're going to have half times the base, which is U, times, make sure you put this in brackets because we're going to be multiplying both those terms. So it's a half times 16 U, oops, yeah, I'll do that, times, no, what am I doing? It's not times, silly me, minus U cubed. Oh, and that does have to be put in brackets. And a half times 16 is 8. So 8U minus a half U cubed. So that's the area of the triangle in terms of U. Now, if you're trying to find the maximum area, so your maximum is found when the derivative, so in this case dA du, okay, because A is basically what where Y is usually, and U is where X is usually. So we're not saying dy dx because our variables are A and U, not Y and X. All right, so taking the derivative of that, which is not hard, 8 minus, bring that 3 out, 3 onto U squared. So that's our gradient function. Now, finding the maximum, we let that equal 0. So your maximum is when dA du equals 0. So we're just going to solve that. Keep scrolling. So 3 on 2u squared equals 8. U squared equals 8 times 2 on 3. And obviously you could do this on your calculator. You don't need to do it by hand, but you do need to show some steps. All right, u is equal to both the positive and negative square root of 16 on the square root of 3. Now we know u has to be, now, keep going down. Now u is between 0 and 4. Therefore, u is equal to the square root of 16 is 4. And then we've got root 3 on the bottom. Okay, so obviously we've got a length, so u has to be positive, but you do need to show this, all right? Because negative 4 on root 3 is an answer, but then you've got to say, well, why isn't it an answer? Because u has to be between 0 and 4, what it says in the question above. Anyway, question C says determine the maximum area of the triangle. So I'm going to have to do this back over here. So we're going to sub in u equals 4 on root 3. Obviously, you can do this on your calculator. Sometimes I just like to do things by hand. Minus half times 4 on root 3 cubed. All right, so that's 8 times 4 is 32, and I wrote the square root of u when it should have been the square root of 3, so I'm going to put that out. Silly me. Just make sure I've done that correctly. Minus a half times 4 cubed is 4 times 4 is 16 times 4 again is 64 over root 3 cubed. All right, so that's 3 root 3. I did have to double check that on the calculator. All right, so half. I honestly should be doing this on the calculator because this is taking me forever. Minus 32 on 3 root 3. I'm just going to go do that on the calculator now because I can't be bothered going any further. But if you were doing this by hand on a, on a exam 1, you would have to obviously get the same denominator. So 32 on 3 root 3. 64 root 3 on 9. You could also do this on your calculator. So just for the benefit of those who want to do it on the calculator, the problem is when I was doing this on the calculator, I was thinking of x when things are in terms of u. It's probably a good idea to always use whatever variable you're using in your calculator. But for this one, what I'm just going to do is our function is 8. No, where are we? The area function is here. So it doesn't matter what version you use, but I'm just going to use 8u minus a half u cubed. So on your calculator, I always can never find it. Calculation function max. And I'm just going to use x if I can, but just make sure you don't put your answer as x. Okay, so 8u minus a half u cubed, I'm just using x. We're going from 0 to 4. All right, so you can see there that the maximum value is 64 root 3 on 9, which is what we got. And the value of u was 4 root 3 on 3. So what they've done there is it's the same answer, it's just rationalized the denominator. So we shouldn't have a third in the denominator, but because this question wasn't asking for the value of u, it was asking for the area, it didn't matter that we kept it as square root of 3 on the denominator. All right, let's quickly get to D. So explain what happens to the area of the triangle as the function f of x undergoes the following transformations. So you can use define in your calculator if you're unsure what happens here with these with this function notation. Although it's in your notes, I remember doing it. Then just on your calculator, define f of x, then write 2f of actually I should just tell you. Okay, so you're defining f of x. And I wrote the area formula here, so oops, don't need all that. Copy that equals, all right, so that's your area of triangle. Oops, didn't do define. Where are you? Define. Okay, so I've defined it. So on your graphing screen, you can just do f of x in 1. Now I think this works, 2 times f of x and f of 2x. So we can sketch all of them. All right, so first of all, I'm sorry, I can't make this bigger. The blue is our original one. All right, what happens with the red one is we've got a dilation from the x-axis by a factor of 2. So that means the height of the triangle has increased, okay, but the width has stayed the same. So obviously the triangle, with your height increasing, the area of the triangle is going to get bigger. Now, f of 2x, we've got a dilation from the y-axis by a half. All right, so you can see the green has kind of become narrower in a way. So the blue is our original, then the green has the same height. All right, so your triangle would have the same height, but your base is halved. So obviously then your triangle would, the area would decrease. Now it's not the area doubles and the, for 2 times f of x, because the triangle just has like a pointier top. Right, so just because you're increasing the height does not increasing the height by a factor of 2 does not mean you're increasing or doubling your area, okay, because your base is also not increasing by the same factor. The base is staying the same. So if we think about the triangles, you've had your original triangle is like that, then undergoing a dilation from the x-axis, the height has doubled, or that's a bit bigger than it doubled, and then for dilation from the y-axis by half, your base is halved, but your height is the same. Okay, so the area has increased for this one and decreased for this one. All right, I think that video is long enough. All right, all the best, girls. Bye.